Okay, I'm Jagadeesh MOODERA from Physics Department, MIT. I want to thank you, all of your organizers, for putting me up here. And in fact, I'm in a different time zone. I'm not in US right now. I'm in India. It's around 2:40 here. So it's a pleasure for me to talk about the work we have done with the team of people, as you see here, Peng Wei, Sujit Manna, Yingming Ji, and Cam T. Law, Patrick Lee. So the other people. So this program we have for many years and supported by Templeton Foundation and ONR mainly. And recently we have some programs started with the NSF and so on. Okay, so here are the people who have been instrumental in getting this working. It started with the theory of Patrick Lee and Andrew Potter, MIT. So they came up with this idea and they had the theory papers. They approached us and then the experiment was done by us. And in fact, started with the Peng Wei. He was with me for almost 5 years as a postdoc. And later on, Sujit Manna joined. So he was also instrumental in STM-based studies in this particular project. And when we had the results, it was actually also modeled to show that what we see is what is expected from theory point of view as well. So that's when Katie Law and Yingming Shi came along. So these are published in the recent couple of articles, as you see listed at the below. And it has appeared in several websites and so on and so forth, applied for patent and so on. So basically it was instigated by the theory by Patrick Lee. So we came up with this idea that one should be able to see the Majorana pair easily on a gold surface state on a particular orientation. So we heard earlier some talk on the Majorana, and essentially we basically know that under certain circumstance, a fermion in a superconductor can separate in space into two parts known as Majorana Zero Mode. So these are fermionic states and they always appear in pair. And the very fact that they're non-local, this is one of the greatest promises towards developing topological qubits. So Kitaway chain, as you must have seen many times before, shows how the Majoranas bound states can form at the end of the wire, superconducting, where the spin degeneracy is lifted. And these are nothing but the quasi-particles with the equal probability of amplitude distribution with electron hole and so on. So we need superconductivity, spin-orbit coupling, and of course, Zeeman energy involved in this. So in our case, we need a heterostructure for this. So, but before I go into our program, we know that there are lots and lots of exciting work in the literature, starting all the way from 2012, Del's group, and then of course Charlie Marcus group. Then on a ferromagnetic chain, both at Princeton and also in Hamburg, a lot of work, nice work. And in the case of topological insulator and superconductor system with a flux lattice, one expects to see a Majorana in the middle. So Fu and Kane have also a model which is for the topological insulator. In all these cases, what we see is these are all based on semiconductor, at least first two of them. These are very complex and they induce superconductivity and they have shown nice results. And then of course, energy scale is on the order of microelectron volt for the spin orbit. Whereas in another case with the STM, we are talking about making chains of atoms on a superconductor. Then it's nice to show the principle of it. However, if you want to scale it up, it's a different story. So what we want to do was, since this field is exciting and then it continues to show exciting results, we wanted to find a system with strong spin orbit energy. At the same time, it is scalable. So first of all, of course, we have to show this Majorana exists and then see how we can scale this up without much complication as others have shown. So that's why we got into this one when Patrick approached us with this new scheme, new platform. So the outline of my talk is that I want to show you briefly what the theory proposal is about. and what are the experimental challenges we have, and how we went about overcoming one after the other. It took a while for us, but nevertheless, we were able to make epitaxial growth of the structure we needed. And we'll show you how we induce superconductivity in the surface state. And one of the most important part is how to tune the Fermi level or the subband of the surface state. And when you do all these things, we have set a stage or platform to see the Majorana pair. And finally, I will show what we expect to do in the future. So this is the theoretical model of what is expected to be seen by Patrick Lee and Andrew Potter. So shockless surface state of the Gold-111 is what we are working on. So the idea is that if you induce superconductivity in the system, we have a new platform wherein we expect to see the Majorana at the end of the wire. So as you can see here, if you create this Gold-111 wire, one should expect to see Majorana descend in that end under the application of a large magnetic field. It enters into the topological regime, and then you should see. The good thing about this system is it has a very large spin-orbit coupling energy on the order of 110 milli-electron-volt. So it's a stable system. It's an ideal system if you want to develop further. And first thing, of course, we have to find Majorana pair in the system. You can see the references here where they published their work in the past. So we set about doing that. Now, let me tell you why this system is important, besides the fact that it has very large rush bar energy, which is on the order of about more than 1,000 times bigger than what is possible with the semiconductor systems. So thing is also, there are a couple of serious problems how to reach there. One is that the Fermi level is way up compared to the band bottom. So which means if you make nanowires, despite the fact that you actually have quantum confinement, you have many, many modes to deal with. For example, if you make 80 to 100 nanometer wide wires, you still have to deal with 100 different modes, 100 different states you have to deal with. So that will actually dilute the effect what we are looking for. So it becomes very difficult to see the Majorana signature. That's one. So we need to find a way to change that one. The second is we need to have a large in-plane magnetic field. So what we have in our STM system is only about 5 Tesla parallel field. That's one of the very unique things we have. And also it is a vector field. Despite that, that's not enough. So these two problems one has to solve in order to reach what we want. We want to move this bottom of the surface state band towards the Fermi level. So as you see in this particular figure here, that is the surface state, as you can see, and that's a rush bar splitting here. And you can use superconductivity and then apply magnetic field. You can have the Zeeman splitting and move the chemical potential in the middle in order to see the Majorana pair. So both the problems we found could be solved if you use europium sulfide on the surface of the Gold-111. So it doesn't seriously affect the surface state. Nevertheless, it actually changes the band to the place where we want. Added to that, it also has a very large exchange field actually being subjected to the gold surface. So it has actually both advantages. It actually takes us towards where we want. So that's where we lucked out. So we had many, many experimental challenges, as we see here. First of all, we are supposed to grow Gold-111, which is smooth and covers the surface completely. But most people who are actually dealing with epitaxial metal films, they know gold is notorious to grow very smooth, very thin layer, which is completely covering the surface. It likes to form clusters because of the surface energy. So that's one challenge. And then, of course, we had to induce superconductivity in this gold surface state. So gold surface state, as you see at the bottom here, is isolated from the bulk band. So that's one of the very strange things about it. That means the conventional way of actually inducing superconductivity by proximity coupling does not work because this is isolated from the bulk band. So whereas the bulk band of the gold can can become superconducting because it is in contact with the bottom, which is let's say vanadium or niobium, whatever we're going to use. So we need to make sure this surface state is acquiring superconductivity. Then, as I mentioned earlier, we had to reduce the EF, or rather lift the surface state band towards the Fermi level. So otherwise, we'll have too many subbands, and which of course dilutes the signature of the Majorana signal or zero bias signature. So good thing about it is the scalable gold wires can be easily formed because there is plenty of work on such things. And that's what we wanted to solve all these things. That's a schematic, theoretical schematic. In the beginning, they thought they can move the chemical potential down or move the band up by a dielectric and an electric field. But we all know that it's not so easy to move the bands on a metallic system by electric field by such a large amount. So in the case of these nanowires, here is a calculated Majorana wave function by Lee and Potter. What we have is, if you have a very wide range, width nanowire of the gold, then the Majorana wave function is distributed all around the edges, as you can see here. Now we start narrowing it down, we see it starts slowly confining towards the two ends. So we have to work towards very narrow wire on the order of at least, say, 50 to 100 nanometer. Then we find that the Majorana wave function confined to the two edges. So that's what we have to do. So it means even on a superconductor, we have to make these narrow wires of the gold. Here is the way we set about the first step. That is, the first step is to grow very smooth vanadium and also the gold 1,1 on that. So we chose vanadium because gold 1,1 matches quite well with the vanadium 1,10. So you can see from the read pattern, it took some time for us to get to this level. We had to essentially tune the growth parameter in different ways to make sure this works the way we want it. So you can see that this is all published, you can find in the literature. So we are able to actually, with this procedure, grow very smooth films of vanadium and gold. As you can see from these kissing fringes, it tells us the surface is very, very smooth. So we are able to create a very smooth surface, smooth film which completely covers the surface. This can be seen in the STM surface topography here. What we have on the left side is a 20 nanometer vanadium layer, which has gold on it. So the vanadium surface, if you look at the atomic resolution of vanadium surface, you can see the atomic resolution here. So it's very nicely forms, and of course, with this the limited scale here, we don't see any defects. It's very well ordered, and in fact, it's nicely formed. So that's very nice. And then you can see the gold grown on the top. It also has a flat surface on it and platelets. And then, of course, if you look at the atomic resolution, you can see the 1,1 surface of the gold. So we are able to get flat and clean and smooth films of this vanadium and gold. So that's a very good thing to do, because if you want to create what we want to do, then we need to start with a very right kind of material. So next thing is looking for the surface state. Since the gold is grown on the vanadium, we want to make sure the surface state is not affected. So the gold film is about 4 nanometers. And if you look at the STM image, so STM scan of this spectroscopy, you can find that the surface state of the gold 111 is indeed intact. We can find surface around 500, something on the order of 500, 550 millielectron volt. So you can see a large drop in the conductance. So then we reach the band bottom here. So surface state we can see is there. So that's, of course, we had to move it down all the way down to this chemical, Fermi level, this band. So that's one of the tasks we need to have. So what we have is a well-defined surface state of 4 nanometer gold on the vanadium. So that's very good. And of course, we make the gold thickness large enough so that this surface state is quite well isolated from the vanadium. So it doesn't directly in touch with that. This is one of the advantages we have in this particular system. Now, next thing is we have to introduce superconductivity into the surface state of gold 111. So we can easily introduce superconductivity in the bulk vanadium because it's in contact with vanadium, bulk gold, because it's in contact with vanadium underneath. So in order to see this, what we have is a structure as shown at the bottom here. It's a complex structure. This is one of the approaches we have taken to create planar junctions. It is not the STM-based one now. So we started with the planar junctions here. So you can see the bottom is vanadium grown on the sapphire and the gold, and they put a barrier of European sulfide. Then you put the aluminum counter electrode. Aluminum is a superconductor below about, in our case, 1.7 Kelvin. So whereas below 4 Kelvin, you can see superconductivity beginning to show up. That is when the vanadium becomes superconducting. As you cool down, you see that in addition to the fact that it becomes more well-defined for the vanadium, you can start seeing peak appearing. And one peak actually becomes two peak as you reach around 2 Kelvin. In other words, initially you see one peak that coming from the bulk of the system, and then as you cool down, you start seeing additional peak. So this is the second peak which comes because of the surface state becoming superconducting in the case of gold. So that's what we have. Now this measurement is down to about 2 Kelvin. And when you have the aluminum becoming superconducting, then it becomes, that's a 2 peak I was talking about. Now, when you go down to 1 Kelvin, because aluminum is superconducting by 1.7 Kelvin, you have a very nice SIS system, SIS tunneling. So we can clearly see all these peaks appearing from the conductance. So this can all be related to various gaps in the system. We have aluminum, which is a superconductor, as you can see here, very nicely defined. And then you have two gaps actually. One is for the bulk, which is a combination of vanadium and the gold. Second one is the surface state of the gold. So when you do tunneling from this system to this combination or heterostructure, you can actually explain all these peaks. To show that these peaks all appear at the exact expected point, we can actually model this after using two density of states, one coming from the bulk, other coming from the surface. When you fit this thing, you find that you can actually derive the gap. Aluminum gap, of course, standard gap, we can easily get 0.22 milli-electron volt. The gold gap comes over to 0.61 milli-electron volt. That is the so-called what we call the bulk gap. Now the surface gap is quite nicely forming, and it is about 0.4 milli-electron volt. So that's a very robust superconductivity on the surface state of the gold. So we can see that we are able to actually induce superconductivity in surface state. This superconductivity on the surface state is not the typical multiplanetary reflection or the bulk in combination with the vanadium. It actually derives its superconductivity from what's called the interband scattering process. So this is the kind of model which has been developed by Potter and Lee again to show that the superconductivity in this 111 surface state of gold has a different mechanism. It's unconventional superconductivity, not the standard one. So the nice thing about it is, although it's not so easy to derive superconductivity in this one, but the thing is, it is slightly isolated from the bulk. It helps in confining the Majorana. In other words, if the Majorana forms in the surface state, since it's isolated from the bulk, it is sort of protected. It doesn't leak away very easily. So that's another advantage we have in this particular system. Now, next, of course, I just want to show you, we can actually scale this gold into any kind of shape and size and any kind of architecture you can make. That's a very nice thing about it. So this is we have many examples of various structures, which is in fact needed for the next phase of the program. You can see that you can make all the kinds of structures here. So we can make any length all the way to even 10 micron long, very narrow wire, 100 nanometers, 10 micron long and all that. So we can have the Majorana pair isolated from each other at any length you want. So it gives us a lot of flexibility in designing this. We can have any kind of network of circuits here that also can be found. So this is very, very nice, because this is one of the easiest way to actually can create a network without going through lots of complex processing steps. So what we have shown so far is we have successfully grown epitaxial gold vanadium heterostructure. We can also show that we have a surface state superconductivity in 111 gold. This is very important. It has a very well-defined gap. Now we need to achieve how to tune the Fermi level, or rather move the band towards the Fermi level because it's far away from the band. So we know that it's around 500 milli-electron volt away. And we have shown the scaling of the Majorana. Next thing would be to move towards STM so that we can actually easily scan the whole thing instead of trying to make many different nano devices. It's very labor intensive and also it consumes a lot of time. So we switch to STM mode to show the proof of principle. In other words, to show that Majorana's pair exists in this gold wire. So then the next part of the work is going to be all STM based and of course scanning tunneling spectroscopy as well. As I shown earlier, here is the structure. We have 20 nanometers of vanadium and 4 nanometers of gold. And then you can see the surface of the vanadium 111, and similarly you can see the surface of the gold. At the same time, you can see this surface state of the gold 111 also. Now, when you cool down to about 360 millikelvin, you can see very well-defined hard gap of the vanadium superconductivity with the gap of about 0.83, delta of 0.83 milli-electron volt. So we know that it has a very nice property as expected, as good as bulk high purity vanadium. So we have a very nice superconducting gap using the STM. Now you can also see if you make nanowires of this gold on the order of 100 nanometers here, then you can also see the edges of the gold very well defined, very sharp edges you can see, and you can also see the surface of the 111 gold still reasonably intact. Now, once again, you see the surface state is intact. It hasn't been destroyed by the processing of this thing. In the case of superconductivity, you can see superconductivity nicely develops on the surface of the gold on top of this one, and you can see the gap formation. So the tip we use is platinum iridium or tungsten. So in this case, we have what's called the NIS tunneling, not like previous case SIS tunneling. So the bigger width of this, so the coherent peaks is because we have a normal metal on the other side. Also, we use a bigger modulation bias to get a good signal. Now, the question is how to tune the chemical potential, or rather move the band. So what happens is when you put europium sulfide on the surface, we found that it does actually move the band way up, all the way from 500 milli-electron volt to about 30 milli-electron volt from the chemical potential. This happens because the dielectric constant of the europium sulfide is very large, on the order of 25. So it actually modifies the surface potential, and so as a result of that, the quantum well state, the quantum well structure of this surface state is actually confined, to lifted way up into the system. And we can clearly see by scanning both on the surface of the gold and just move on top of the europium sulfide, you can go back and forth, you can see the difference in the two. And the additional thing about the europium sulfide, it provides a very large exchange field in addition to moving the chemical potential. Now, that is the basic principle of it. In other words, the exchange interaction of the europium sulfide with a metal in contact with it is shown here. This is a scheme which is kind of been described long ago by Deschain's group and Sarma way back. And what actually happens is this europium sulfide has this aligned europium ions, which are very large magnetic moment. So the conduction electron interact with this aligned moment. It creates a very large exchange interaction here. And as a result of that, the exchange field can be anywhere from few Tesla to hundreds of Tesla. So we have a large inbuilt exchange field present by just having europium sulfide in contact. There are lots of work we have done on this particular kind of combination with different superconductors and topological insulator and so on and so forth. And one of the earliest one is Paul Tedros' work way back in '86, where he showed first time that with europium oxide, you can have a very large exchange field. Where the europium sulfide is even better, it creates even bigger exchange field. And there is a review if you want to see, and also recently you can see in PRL this particular work. So we have a system which is a very nice, nicely forming compound, ionic compound, which has not so much of defects. It's easy to form, easy to evaporate, and then it can create a huge exchange field at the interface exactly where you want. It doesn't it doesn't leak out to everywhere. It just confines itself. So we can have a local exchange field on these systems. So now we have both things there. That is, we can move the chemical potential. For example, here we see the islands of the European sulfide because this is only about 2 monolayers thick. So we purposefully created this way because we wanted this island. Complete coverage of this could become a problem because in STM, so the signal becomes rather noisy and we won't be able to see small features because we are dealing with very small currents. So when you have this island structure, then you can actually probe around the islands, go around the island to see what's going on. So look for the Majorana. So this is the nanowire. And in this little segment, what you see here is where this islands you can see. These are exactly 2 monolayers thick. Now on the right side, what we have is a comparison of this surface state of the gold 111 by the scanning tunneling spectroscopy. This is without, this particular one is without the European sulfide, that is more far away from the island, and this is done on top of the island. You can clearly see this edge of the band is moved all the way towards the EF. So that means you have moved the bottom of the band way up towards the chemical Fermi level. So that is exactly what we wanted. So instead of dealing with hundreds of modes, we now have just a few modes, anywhere from 3 to 5 modes to deal with. Now we go down to very low temperature, like 360 millikelvin, and scan around the island. You scout around the island. Of course, we do many islands. For example, this one, all the way from 1 to 8, go around. In zero field, you can see a nice hard gap formation in all cases, in every point here. Then apply magnetic field along this direction. Then what we find here, in these regions, you still see the hard gap, as you can see here, 7, 8, 9, 4, 5. Whereas exactly opposite each other in two locations, you see peak appearing. This peak starts appearing beyond about 3.5 Tesla, which means there's a threshold field when they start showing up. So when the field is not there, then you see a hard gap. And applying a large field, when the field reaches this level, then you start seeing this. So this is a peak we attribute to the Majorana pair formation. So basically, this is what you expect. So in our case, instead of just a gold wire, we need to have, of course, very large magnetic field. Meanwhile, it will destroy the superconducting gap of the bottom layer. If you have a local magnetic field exchange field present, then actually you can create you can achieve this topological state in a lower applied field because the rest of the field comes from the European sulfide. So here we see the signature of first signature of the Majorana peak, zero bias peak. Now, this is even more dramatically seen when you have an island. In the previous case, actually, you had an island in the middle of the wire, right in the middle of the wire. Whereas next one, we happen to have an island. It's about 60 to 80 nanometers, 60 or I don't know, 40 or 50 along this direction and 80 in this direction. And you have that. Once again, you can actually scout around island all the way around it. We cannot scan on top of the island because it becomes very hard from the signal to noise ratio. So we have to get very close to the island. On the gold, we can actually scan. So when you do the scanning in zero field, you see perfectly formed hard gap in all cases, everywhere. Now apply magnetic field, say in this case again 4.8 Tesla. What you find is in all these regions from 2 to 7, all these regions, you still have the hard gap. Nothing has changed, just a little bit of filling of the gap region by the states. Whereas in position 1 and 8, you find a huge increase in the conductance at the zero bias. This is clearly showing that there's a zero bias conductance peak appearing, which representing the Majorana pair in the case. So the European sulfide actually forms very nicely, very ordered structure, as you can see here. So very well ordered. It also epitaxially grows even at room temperature on the gold. So we have a system now. With the European sulfide, you can actually have this Majorana pair appearing in these corners. This is interesting because it seems to like these corners. Now, this can be also simulated by theory that we'll come to in a second. Whereas before that, let me show you how it actually evolves as a function of field at the same time around the same field. So for example, on the left you have location 1, you track it down as a function of field. You find that around 3.5 Tesla, this peak starts appearing. On the other hand, on position 8, also we have the same nice hard gap, and then we start filling in, and by about 4 Tesla, you can see the appearance of this peak, central peak, zero bias peak. So there's a slight variation between these two things. So this is sort of expected in our system because this Majorana actually formation is very strongly dependent on the location in some sense. It is a plot, 2D plot of actually what the conductance is like as a function of magnetic field. As you go up in a field, you see the gap starts closing. The gap starts closing, and then the topological gap opens. When that happens, you can see the Majorana forming in the middle. So this transition is not very sharp, it's rather broad. So this is sort of dictated by many things here. For example, the rate of the zero bias peak is actually controlled by the tunneling rate. It's a ratio of tunneling from the STM also to the quasi-particle poisoning rate. So the quasi-particle poisoning is very high, which is the case when you actually go through the transition, then this signal is going to be very small. Now, the large reduction in this could be expected near the topological gap. That means you have this other states coming closer to the gap and then start introducing its own signature to this and dilutes the Majorana signal. And of course, you can, if the sub-gap states are actually very close, then you can have some excitation from the topological Majorana state. So as I see here, as you go away from this topological transition point, you go to higher fields, then actually the peak starts improving. That means the gap starts increasing. So when the gap starts increasing, you have less influence from these sub-gap states. So this is one of the places one has work to do, in a sense, how to improve this sub-gap poisoning of this Majorana. So that depends on the gap and how you're able to have a very clean system built and so on and so forth. So with this kind of behavior here, you can clearly see that it's not exactly possible to have the same field wherein both the locations have the Majorana appearing. There can be slight variation, as you see. Now, in simulation, as you clearly see here, if you have an island in the middle, then the Majorana's wave function is sort of distributed along the edges. So which means it's more of a rounded, it's not very sharply well defined. On the other hand, one of the islands as we have, this is all actually based on exact what we have and the modeling was done. What we have is the Majorana wave function actually is confined towards these corners. So this can be sort of understood because that's where the chemical potential has a large step, because this part is the gold. So there's a step of the gold wire, and then it's gold wire, there is no gold wire in this side. So this edge is actually between the European sulfide and the gold. So the moment there's a huge step, then the Majorana confines itself here. So this gives us an idea like how to actually precisely define where to find the Majorana by properly designing the system. Now, we want to know how far it can actually last. For instance, if the field is applied along this direction, then you want to see the Majorana. The best we can do is go very close to this edge of the European sulfide, because we cannot work on top of that. Although Majorana actually likely forms right there underneath here, but the leaking the wave function is enough for us to pick up with the STM. Then you move away from here like this, as we've done here. You move away from the edge, you find that the signature goes going down, and by about 10 nanometers away, this Majorana signature has died off back to the hard gap. Same thing if you go away in this direction as well, as I mentioned earlier. So the Majorana actually seem to be confined within about few nanometers. So the localization length or the coherence length of the Majorana we can expect to be on the order of 8 to 15 nanometers. So it is rather confined. That also tells us that in a small island such as this one, how we are able to see the Majorana, because they are so close to each other. There is some hybridization But of course, the temperature is not enough, plus our resolution not enough to see the splitting and so on and so forth. So this is theory simulation. So these two I explained already to you. And what you see here is this is what I was talking about. In this conductance as a function of energy, what we find is the Majorana pair here. These are all the subgap states I was talking about. Right at the transition, these are very close to this one. There are lots of them. As you move away from the transition, go to higher and higher field, this topological gap increases. It increases, you can actually get a more well-defined Majorana pair. So simulation shows that instead of 350 millikelvin, if you go to 700 millikelvin, it almost reproduces what we see here, as you can see on the top. So this extra broadening is coming from because we use a higher modulation, and also some noise is introduced, maybe part of the quasi-particle poisoning as well. So whatever we see experimentally can be simulated by theory. That means what we have in the theory expectation is exactly what we see. So that tells us that we are able to see the Majorana pair in this system. Now that is the kind of equipment we used. That's our MBE to grow this layer system. One of the major handicap we have is our STM is sitting on the second floor. It doesn't have any very fantastic isolation or anything. It is sitting on an air table in some sandboxes. So that makes us rather very nervous. We could work only at night between 10 in the night or something like that till morning 6, because about 100 meters away, 50 meters away, there's huge building construction MIT, and the amount of noise they're putting big pillars. So that was actually a big restriction. That's the reason we couldn't scan the whole area and all that. We could only do what is basically needed. So our STM has a very nice in-plane field, and it has a rotating top stage which can align the field in any direction with respect to the nanowire. So what we found was the field is perpendicular to the nanowire. We don't see the signature. We only see the signature when the field is parallel to the nanowire, as expected. So our stability, despite all these things, is pretty good, 1 picometer, but it needs some improvements if you want to use spectroscopy in a larger scale and more careful and so forth. So that brings to the summary, and we are able to see Majorana pair as expected from theory. So we were able to confirm what is predicted. And you can see the surfaces of Gold-111 indeed acquires superconductivity in a very interesting manner compared to the conventional way. So it's a noble metal, it's a very stable system, so we can have a very nice fabrication of any kind of network we want. Since the Raj-Pasmanov bit splitting is so large, on the order of 110 millielectron-volt, it's a very robust Majorana. We can actually operate at much higher temperature. Instead of 10 millikelvin, we can operate almost half a Kelvin or something. So that's another advantage we have. So what we think is we have an excellent new platform for complex scalable qubit development in this particular case. So we have a new program. It's just started like last month. It's an NSF-funded program. So basically, we are looking to develop topological qubits. We all know we need quantum computers for the future because computation is becoming very intense. So it can actually define and it can modify a lot of things what we do. So here are two pictures, which I borrowed from some internet. This particular one is a Google quantum computer, which is 53 qubits. You can see the number of cables and all that. And the other one, which is a conventional supercomputer, can take about 2 to 3 days. This system can operate in about 300 seconds. And you can see the huge change in the time scale and also power required. Now, this kind of cabling is okay for up to some few tens of qubits. But if you want to develop a system which is much larger density of qubits, then likely this is not the approach we can take. So our goal is to, if you can build a robust and qubits quantum computer that can do a huge amount of good to the society. So for example, basic thing is that whatever that is there right now in the formation of quantum computers, there's huge amount of problems to confine this qubits. It has a lot of leakage and a lot of decoherence. This is a big problem. And of course, error rate is 1 part in 1,000. That's the big issue actually. So you cannot easily scale it up. So it's a problem. So whereas if you compare that to the transistor, it's like 1 part in 10 to the 20. Here we are at 1 part in 10 to the 3. So that's a problem. So we should find a way to improve this this kind of decoherence and also make it more robust. So that's our goal with this topological, I mean the Majorana based ones. So that's what we want to do. So basically we want to create this topological qubit based on the Majorana and try to approach this program with what Liang Fu has predicted, or rather theoretically postulated possible. So the goal is to create this kind of architecture, a measurement based way to actually look at the parity of the system. So that's how we plan to do this program. So this will actually, it will definitely reduce the error rate substantially. And also, we don't need that many cables as I showed in the previous slide. So we can operate just with a standard transport measurement system, which may be much less number of cables into the system and also much finer wire. So, but it's a very high risk and high reward program. So good thing is we have a platform now which can help us take towards the topological qubit. So with that one, I want to thank you very much for your attention.